This is problem number 21 in section 3.4 about the second derivative. Looks like our camera's a little bit out of focus. Okay, looks like it's all right. So let's look at problem 21. We want to find the second derivative, places where it's concave up, concave down. Generally trace the function and see what it looks like. So we'll start by finding the, well, first let's notice that it's a polynomial, so it's defined everywhere, so there's no place that we have to worry about asymptotes and stuff like that. There's no place where the denominator is going to be 0, so that's a nice thing. So let's find the first derivative and see what that tells us, and then we'll find the second derivative and find out about concavity. So I bring the 4 down, I'm going to get 2x to the third plus 6x squared. And the second derivative, is just as easy. That's going to be 6x plus 12, no, 6x squared plus 12x. All right? So we can figure out a lot of stuff here if we just factor these. So here, if I factor out a 1/2 x squared, what's going to be left here is going to be an x squared, and then plus 4x. I'm sorry, plus 4. Well, I guess really what I want to factor out is an x cubed, don't I? I'm going to factor out a 1/2 x cubed, and then I'm going to get an x plus 4. So we can see that it's going to have roots. There's going to be roots of the original function when x equals 0 and when x equals -4. So that's a big deal. We know it's going to cross the x-axis at 0 and at -4. So let's start graphing this and see what it tells us about it. So here we've got 0. There's going to be a root, and 1, 2, 3, 4. There's going to be another root at -4. And we'll have to figure out what the concavity is doing and stuff like that. The first derivative, we can factor that also, so that's going to factor as, we can factor 2x squared out, so I get an x plus 3. So it's going to have critical points at 0 and at -3. So here's the first derivative. It's going to have a critical point at 0 and at -3, so those two places it's going to equal 0. It's going to be defined there. It's just going to equal 0. To the left of this, if we take an f prime first derivative over here where x is less than -3, this is going to be negative. That'll always be positive, so it's going to be negative over here. Between the two, if I make it like positive or -2, this is going to be positive, that's going to be positive, so it's going to be positive in here. And then to the right of the y-axis, where x equals a positive number, it's going to be positive over there as well. This is an interesting function, because notice it comes up here, it's going up at this point, and then it's 0 there, but then it goes up again over here. This point over here seems more intuitive. It's coming down, reaches 0, and then goes back up. So it looks like something's going on here, but something weird is happening at the origin. Okay, concavity. Let's look at the second derivative, and we can, we can factor out a 6x here, and then I have x plus 2. So here it's going to be the second derivative. It's going to be concave up or down, depending on the sign, of course. So if I make x like -4, something like that, this will be negative, this will be negative, so the whole thing will be positive over here. Where are the points of inflection? Where is this thing equal 0? At -2, so these are points of inflection where x equals 0 and at x equals -2. So we'll start with those points and compare the sign of the second derivative in the intervals on either side of these points, okay? So here at -2 it's 0, and at the origin it's 0. So they have points of inflection, or we don't know what's going on there. Changes in concavity But remember, you have to check to make sure it really does do that. So let's look at over here to the left. So if I make x smaller than -2, like -3, this will be a negative times a negative, which makes it positive. So here it's going to be positive. So remember, that means concave up. -1, if I put a -1 in here, this is positive, but this is negative. So right in here it's negative. And then if I make x positive, then both of these are going to be positive, and the concavity will be up over here. So it's going to be concave up here, concave down here. And points of inflection either at -2 or 0. But we have to check that, so we do need to check that. All right, so what's the function look like? Well, we know it crosses the origin at -4 and 0. So you probably want to check a critical point. What's the value of the function at -3? That's where the first derivative equals 0. So let's find f at -3 is going to be -3 to the 4th is 64. Positive 64 over 2 would be 32, and then plus -3 to the 3rd would be -27. Times 2 would be -54. So let's see, what is that? 22, -22. So here at 0, it's going to be down here at -22. It's going to be coming down like this. It reaches 0 at that point. It's concave up right here. It goes back up. At this point, -2, when f is equal to -2, let's see what it is there. This will be -2 to the 4th is 16. Half of that is 8. And then plus -2 cubed is -8 times 2 would be -16. So here it'll be -8. At this point, -8 and -2 is where it changes from being concave up to concave down. So right there, it's concave up over here and concave down there. And then over on the right, so it reaches a slope of 0 right here at the origin. So it goes flat there for a second. And then it goes positive again. It goes back up like that. Concave up, concave down, concave up. So the function looks something like that, I think. And we can verify that with the graphing calculator.